Hello everyone, this is the fourth part of our review of the SMO Open mock paper. We'll be looking at questions 16 through 20. As I mentioned in the earlier part, that if you had been trying the paper in sequence, it is possible you ran out of time around question 15. And if that's the case, I would still suggest you try these questions in an untimed fashion before coming back to this video, because there are some interesting ideas here which feel it's a bit of a waste if you were to just see it without having given it some thought. Let's get straight into question 16, which is a question on vectors that is not as tedious as many other vectors problems in recent SMOs. UVW are vectors with magnitude 22 and 22 respectively, and V cross W cross V plus 2U is equal to the 0 vector. Let alpha be the angle between U and V, and beta be the angle between V and W. Find the absolute value of 22 cos alpha plus beta. Right, so we can start off with understanding this equation here, right? That's really the heart of everything. Remember that whenever you have a vector equation, you have two different perspectives you can take. One is to write it in terms of components, and the other is to simply look at it in terms of the magnitude and direction of your dot or cross products. I think I'll prefer the latter here. I don't really want to split it into components, and furthermore, things like angles usually are not so useful when you're talking about components. It's more of like the explicit cross product and dot product in terms of magnitudes and sine and cosine. Those definitions are more useful here. Now, the first thing that I would notice, I can just move the 2u to the other side to get negative 2u. Sorry, that looks very confusing. Is that u is equal, u is in the direction of v cross w cross v. Now, this means that u is a normal vector to v, or rather u and v are orthogonal. So if u and v are orthogonal, it just means that alpha is 90 degrees. That's the first thing. Now we need to get beta. Beta is the angle between V and W. There's nothing to equate V and W because V and W are on the other side. So now we have already looked at direction, we can look at the magnitudes. Now, V cross W is perpendicular to V because, well, that's the meaning of V cross W. So if V cross W is perpendicular to V, then the magnitude of V cross W cross V is just going to be the product of their magnitudes. This is useful because I already know the magnitude of V and W, and the cross product would further give me, well, the sine of the angle between them, which is beta. So it would be 2 times 22 sine beta, and then times 2 again, which is 88 sine beta. Meanwhile, the magnitude of negative 2u is just the same as the magnitude of 2u, which is 40. Mu, sorry. The magnitude of 2u is 40. So therefore, it tells us that sine beta is 40 over 88, which is 5 over 11. Now let's come back to here. cosine of 90 plus beta is just equal to sine of negative beta, because sine of 90 minus this, which is sine of negative beta, is equal to negative of sine beta, so negative 5 over 11. And so your answer is just 22 times this, and you take the absolute value, which is 10. Sorry, this is kind of going in all different directions, but sometimes for vectors problems, you don't need to blast open a bunch of components. You just look at the direction, and then you look at the magnitude and see what you can extract out of both of those separately. Alright, question 17. What's the remainder when this sum of 99 powers is divided by 101? Now, this is not really very difficult, surprisingly enough, as long as you know some ideas for modular arithmetic. Take note first that 101 is prime, so we are not going to simplify this any further, nor indeed do we want to. Now, the first thing to note is that whenever you have these odd powers, it is nice because adding all of these gives you some symmetry. So here's what I mean. Right? When you have 1 to the 99, and I first will handle the whole thing, which is up to 2022. I'm going to just break it into blocks of 101, and there will be 20 blocks of 101. Blocks 101 meaning from 1 to the 99, 2 to the 99, all the way to 101 to the 99, with a couple of leftovers outside. So the two extras are again 1 and 2. Now for 1 to 101, why I say that this is nice is because we can go up to 50 and then reverse the rest of them. So 51 is negative 50. And then 52 would be negative 49 and so on. So all of these are going to cancel off because the power is odd. So you just get a negative. And the last one will be 0 because of the 101. So this portion entirely becomes 0, which means you are just left with 1 and 2. Or rather 1 to the 99, 2 to the 99, which is 1 and 2 to the 99. So this leaves us with just a tiny problem, which is what's 2 to the power of 99 modulo 101? Now we know from Fermat's little theorem tells us that if we took 2 to the power of 100, pity, right? We wish that it were 99, but no, if we took 2 to the power of 100, that is precisely 1 modulo 101. So, how do we apply it to 2 to the power of 99? Well, that's surprisingly not too difficult, because it means that in a sense, we want to divide both sides by 2. I can't really divide both sides by 2 in a traditional sense, but I can write 1 is also 102. So now I divide both sides by 2, and I can say 2 to the 99 is 51 mod 101. Now there's something a little subtle here, which is that when we're dividing by 2, the reason why we can do that is that 101 is odd. Right? If it were even, then you can't say that. For instance, if I said that 8 is congruent to 6 mod 2, I cannot divide it and say 4 is congruent to 3 mod 2. That is obviously bogus. But here, this is okay. So therefore, the entire thing reduces to 52 modulo 101. Pretty nice. Question 18 is a very simple idea once you have heard it, but it's pretty difficult to go in that direction. If you are an experienced competitor for the SMO, you have seen many questions of, here's an expansion, find something about the coefficients. It usually involves substituting something. But that isn't so successful here, because unlike the usual, where you're just asked for, let's say, the sum of coefficients, then you put x equals to 1. This is the sum of the square times the coefficient. So you are asked basically for a1 plus 4a2, I should say, plus 9a3 plus 16a4, and there isn't really an obvious substitution that will work here. All the way up to 10,000 a100. You need to figure out, how am I going to get from 3x minus 2 to the power 100 equals to this expansion to somehow get these kinds of square numbers on the coefficients. And that is obviously not an easy task. Now, you probably can tell immediately that just by doing substitutions, you're never going to get that. Because if we do substitutions, we keep getting exponentials, not squares, which is polynomial, but exponentials. And we don't really want exponentials here. So how do we deal with that? Now, the surprising answer is that we're going to differentiate both sides of the equation. So if we differentiate the left side using the chain rule, you would get 300 3x minus 2 to the power of 99. Now, what happens to the left hand side? Well, a0 disappears, which we don't mind. And then you get a1 plus 2a2 and on all the way to 100, sorry, 2a2x, it's important, all the way to 100, a100x to the 99. Hey, that's not bad, because at least we have gotten some linear coefficients onto that. How do we get to the quadratic? Suppose you have guessed it by now, we differentiate the second time. Take the second derivative. So we take out a 99, a 3 again, and you get 89100, 3x minus 2 to the 98, a1 disappears, you get 2a2 here there was a 3a3x squared, so now it becomes 6a3x. And then you would have a 4a4x cubed You add that in, you will get 12a4x squared. Okay, that's really convenient, isn't it? Because it perfectly adds up all the way to the end, and the end would be 9900 a100 x to the 98. So all we need to do is actually to substitute x equals to 1 into both and add them up. So let x equals to 1 and then sum. The reason why x equals to 1 is fine is because 3x minus 2 is also 1. And you would just get 300 plus 89100 is precisely the thing you want. Apologize, my laptop is crumbling under the weight of too much annotations. So, apologies for the lag and the awful handwriting. And I write too quickly, then it just becomes a blob. So I have to write really slowly and in an unnatural pace. So sorry about the mess. But you see that it just lines up perfectly, right? You get A1, you get 4A2, 9A3, 16A4, and all the way to the end with this 10,000 A100. Okay, question 19. The roots of this equation are r sine alpha, r sine beta, and r sine gamma, where alpha, beta, and gamma are all between negative 90 and 90 degrees. Determine r times alpha squared plus beta squared plus gamma squared. Clearly, this doesn't have any real meaning, right? Because alpha, beta, gamma are angles. You never ever square angles. That's pretty nonsensical to square an angle. So it has no significance. This is just an answer extraction. Now, perhaps if you see something like this, you are quite tempted to say that I'm going to just use Vietas, write some equations down relating the r sine alpha, r sine beta, and r sine gamma, and then hope for the best. Which can work, but it would be pretty difficult to solve those systems of equations. Now, instead, one thing that you can notice is that there is no x squared term in this equation. For those of you who know Cardano's formula, this is called a depressed cubic. Not in the sense that it's very disappointed, but in the sense that there is no x squared coefficient. Now, once we have this, what it allows us to do is actually quite nice. If we so-called normalize it, we can normalize it until it becomes some multiple of your triple angle identity, which only involves sine cube and sine. So please recall the triple angle formula, which is also in this rough framework. Alright, I have that in the wrong order, don't I? Yeah, this is the one for cosine, sorry. The one for sine is the other way around. Let me just swap around the orders. It's 3 sine theta minus 4 sine cube theta. Now, I was thinking, every time when I write these identities down mentally, I'm always a little concerned that I have it flipped over. So what I do is I just put in some special angle like theta equals to 30 degrees to just, check whether I have it right. And that paid off here because I actually had it wrong. Okay, so now we need to adjust it so that the portions here hopefully look kind of the same as in this fashion. Currently, the ratio of these two coefficients is 1:12. And here it is supposed to be 3:4. So it means that we are off by a factor of 9, right? So this should have 3 less, and this should have a 3 more. So in order to have a factor of 9, what I need to do is to replace x by sort of 1/3 x, if you will. And how I'll do that is to let y be 3x. To kind of absorb some of the factors of 3 to give me what I want. Okay, so if we do that, we will need to divide 27 from here, and you would get 8 over root 3 y cubed minus 2 root 3 y plus 1 equals to 0. This is already in the correct ratio. I will just multiply by square root 3. I'll shift this over and divide by 2. And that will now be in the correct form as that. Now what I'm doing here is I'm not really caring too much about r sine alpha, r sine beta, r sine gamma, but I have inadvertently kind of found r. Because now if I let y equals to sine theta, I would get my triple angle formula, which usually should give me 3 solutions for the value of theta. So sine 3 theta is root 3 over 2. And we know that sine 60 degrees is square root 3 over 2. So 3 theta could be 60 degrees. It can also be 120 degrees. And you can go backwards by 360 to negative 240. Why I'm doing this is because I'm supposed to make the angles between minus 90 and 90. So here I got 20, 40, and negative 80. Okay. Let's go back and deal with all the substitutions. Now it means that x is equal to 1/3 sine theta, and x equals to 1/3 sine theta means that x equals to either 1/3 sine of 20, 40, or negative 80, which I will just very informally write it as 20, 40, negative 80. This is mathematically nonsense, but you know what I mean. And the good news is simply that we have found out r is 1/3. And we have found out these are alpha, beta, and gamma. So just substitute in to our final expression. 1/3 of 20 squared, 40 squared, and 80 squared. And you would get 2800. This kind of trick substitutions are not obvious, but I guess the reason why in this question is not a surprise is that you are asked to find solutions in this form after all. It's just that you will need to kind of mash it until it looks like something where we can use an identity. And because there's no x squared, there's only x cubed and x, the triple angle identity is the most closely associated one. Finally, question 20. Now, I have to say that for question 20, the idea of it is pretty close to an old IMO plot in this question, But without having to give a proof, it is not that difficult to come up with an answer. So we are asked to find the shortest possible sequence of positive integers x1 to xn such that if we multiply together all of the numbers plus 1, it is 2022 over 55 times all the product of the numbers themselves. In other words, the ratio of them is 2022 to 55. An easier way to work with this would be to bring the x1, x2, xn over and just write it as a product of fractions. And just do this all the way to xn. Now, you want to get to this in as few steps as possible. In other words, multiply as few fractions as possible, and all of these fractions are just in the form of like 3 over 2, 4 over 3, 5 over 4, and so on. You realize that you need to use as many of the big fractions as possible, because otherwise it's going to take forever to reach here. As a quick estimate, 2022 over 55 is going to be 36 point something. So we need to get as close as we can using as few terms as possible. Now, one term that we can say is that, well, 2022 is 2 times 3 times 337. So you need a dedicated fraction here to give you 337. So one of them will be something like 337 over 336, or maybe a larger multiple of 337, like 674 over 673, or something like that. Right, so you have one of these that you have to take from here. If we took this one, which is the biggest of those categories, what we'll be left with is 2 times 3 times 336 over 55. So 2 times 3 times 336 over 55 means that we'll need the rest of the fractions to multiply to 2016 over 55, which is still 36 point something. Now, the bound that we have would be that at least I need enough fractions to get to 36 point something. And in order to do that, I need at least 36 fractions, right? Because I need 36 or more fractions. Because the largest product would be just 2 over 1 times 3 over 2 all the way to 37 over 36 is 37, right? This is the maximum I can go to. So I need at least 36 fractions. If I do 35 fractions, I'm not going to have enough. So maybe a better way to write this is to say that with 35 fractions is not enough. And can we do it with 36 fractions? The answer is yes. As long as we satisfy the 55, because 2016 has a lot of nice small factors, we just need to satisfy 55. And so what I would do is just to use 56 over 55 as one of my fractions. Right? And if we use that, we are left with 2016 over 56. And 2016 over 56, conveniently enough, is exactly going to be equal to 36. So that is perfect, because then you use 35 fractions for this. Right, this 35 fractions which I've just written below. Okay, so we need to be very mindful of what we have used and what we have just remarked on. So we have used 1 here, 337 over 336. We have used 56 over 55, and we used another 35 fractions. And so if we use that, in total, this is 37 fractions. Yeah, so the value I've chosen here, 2022 or 55, is such that you just keep on persistently going for the best case scenario. This is sort of what we call a greedy approach, meaning that I want to pick the biggest fractions, which are 2 over 1, 3 over 2, 4 over 3, and for the most part I do that. The only time where I know I cannot do that is I need to satisfy the 2022 and I need to satisfy the 55. So this is the only way in which I can satisfy those, but once I've satisfied those, the rest of them just perfectly fit. So this doesn't have any mystery over whether it's the best, because you took the biggest one every time. Alright, so that's it for this video. Do stay on for the last video tomorrow, where we will go through the last 5 problems. The last 5 problems are probably the most tricky ones from a proving perspective, but many of them can be half solved and half intuited. So stay tuned for that, and I hope to see you then.